real quick. Okay, so we're looking at number 1. So in the introductory activity, so that was what you did last week, the sphere was assumed to be rolling. So that means it's rolling. Woo! So would the theoretical velocity of a sphere increase or decrease if it slid down the ramp instead with no friction? What do y'all think? Increase or decrease? Okay. Decrease. Okay. Can I ask y'all why? Why do y'all think? Why do you think a sliding block would increase or decrease? So Juan, let's start with you. In velocity. Okay. Thanks for being honest. What about you, John? It doesn't do either? Okay, so it would stay the same. Okay, same velocity. All right, so let's talk about rolling motion. That's something that we haven't really studied before. We know about things sliding down a ramp, but with rolling motion, what is it that makes an object roll? What do y'all think? Inertia, okay, so rotational inertia. What? I'm looking for a different answer. So what about it makes it roll? What, the shape? Okay. Yeah, so a spherical object definitely helps it roll. What else? What else? Gravity. Yeah, so gravity pulls it down. What did you say, Sean? Yes, yes. So that's probably a question that you really never get, like, why do objects roll? I don't know, because they roll, right? So it's really because of friction. So we're going to learn more about that in the last unit, but for right now, it's important to note that friction is what helps it roll. So let's say we had an icy hill. We don't really get icy hills in Texas, but let's say that you were just lying down on the hill and it was icy. So if it was icy, would you roll or slide? Slide, because it's really slippery. There's no friction. Okay, so if it's icy, there's no friction, or very little. Okay, so you would just slide. But let's talk about if you went to the hill in Herman Park, the amphitheater. Have y'all ever like rolled down that hill? Yes. Yeah. So if you're on that hill, can you even slide down that hill? No, you can't. It would hurt if you tried. Yeah, so probably shouldn't slide. You should probably roll. So if you're on a rough hill, so there's going to be friction, you're going to be rolling. Whee! Like whee. Okay. So that brings us back to this question: would the theoretical velocity of a sphere increase or decrease if it slid down the ramp with no friction? So it's talking about a sphere sliding down the ramp with no friction. So if the sphere is on the ramp, it wouldn't roll because there's no friction. So let's look at our answer right here. So in order for something to roll, there must be friction. If an object rolls, then its velocity will be less than a sliding object on a ramp with no friction. Okay, so that would be the answer. And then deriving the formula, we're going to derive it in the second question. Okay, let's go on to question number 2. So question number 2 says use equations 1, 2, 3, 4, and 5, but we're just going to use 1 and 2. So 3, 4, and 5, they have to do with rolling objects. We haven't learned it yet, so we're not going to use it. And we're going to talk about the velocity of an object, of a block sliding down a ramp. So something that's not rolling. So the block is not rolling. We're able to calculate that. Does anyone remember how to calculate for the velocity of an object? That starts with potential energy that turns into kinetic energy. So if you were to start this, what is the first equation that you would write? Okay, before that one. So a hint, it would be the conservation of energy equation. So whenever you see conservation, what does that remind you of? Something that is being, not exactly Newton's second law. So if you're conserving something, you're saving it, right? So if you're saving it, then the first equation you would use would be E equals E. So everything that the object starts with, all the energy that the object starts with, will have to equal all the energy that the object ends with. Okay. Yes, initial energy and final energy. So this way, there's no energy being lost, and that really defines the term of conservation of energy, where energy is being saved. Okay, so from here, we're going to go ahead and look at the next equations. So it would be potential equals kinetic energy. So the object starts with potential energy, and then it ends with kinetic energy. And then from there, chances statement of mgh equals 1/2 of mv squared. I'll go ahead and zoom in. And then from there, you can derive velocity. So algebraically find velocity by looking at the masses, and the masses cancel out. And whenever the masses cancel out, you can go ahead and find velocity. So I just skipped a few steps here, and this is your ending equation. And the equation in black, I replaced little h with big H. And the reason I did that was because in the question, it told me that h was capital. So I just replaced little h with big H. It's just a small detail. So h, that is going to represent the height of either the ramp or the table, depending on what you define h as. Okay, so number 3, examine the formulas derived in number 1 and 2. For a sphere in a box moving down a ramp, which variables can be manipulated to increase the horizontal velocity? So our goal is to increase horizontal velocity. But we have an equation for velocity, and that is going to be v equals square root of 2gh. So knowing that, what are variables that you can change to manipulate velocity? The height, okay, so you can change the height. What else can you change? Okay, so some people might say the angle of the ramp, but whenever you look at the equation, does it include theta, which is angle? No, it doesn't. So the only other thing would be gravity. We can't really manipulate gravity, but let's say we took this object to like Mars or the moon. So that way you can manipulate gravity. So knowing that, you can discuss methods to change the variables to increase the horizontal velocity. So tell me, what can I do about gravity or the height to make the velocity faster? Okay, let's go on to number 4. So I'm just discussing it and leading y'all to the answer. So number 4, consider 2 spheres, one of mass m, the other of 2m, held at 1 meter above the ground. If the spheres are released simultaneously, which sphere will hit the ground first? Otherwise known as which sphere will go fastest. Okay, so the only difference between the spheres would be one is lighter than the other. So do you think that there would be a change in velocity between the two, or no? So shake your head or nod your head. So would would the lighter sphere hit the ground first? Yes or no? Okay, some people say yes, some people say no. So whenever we looked at the equation up here, whenever we were deriving the equation, so whenever we were deriving the equation, what happened to mass? They canceled out. So does mass matter in terms of velocity? Does mass matter in terms of velocity? No, it doesn't. It does not, because it's canceled out. So because it doesn't matter, then that means you should decide which sphere will hit the ground first and which sphere will be traveling faster. So if mass doesn't affect velocity, then velocity won't change between the two. Let's go on to number 5. So number 5 says 2 spheres are held in place at the top of the ramps. Letter A, which sphere has the greatest potential energy? So letter A and B, so look at it and decide, and then I'll ask y'all to raise your hand for A or B to vote. So if you say letter A, raise your hand. Which one has greater potential and energy? If you say letter B, raise your hand. Okay. Third option, who thinks both of them or neither? Okay, yeah, so the answer is actually both of them have the greater potential energy, or neither. Neither have a greater potential energy. Why? What does potential energy rely on? The height, mass and height, and gravity. Okay, so the equation U equals mgh, where U is potential energy, mass is mass, and then height. So they both have the same height, therefore same potential energy. Letter B, which sphere is traveling faster at the bottom of the ramp when released? So I'll give y'all a second to think about that, and then we'll vote again. So this time I'll give y'all the option of neither as well. So A, B, or neither. Okay, let's go ahead and vote. If you think A, raise your hand. If you think B, raise your hand. If you think neither, raise your hand. Okay, all right. So the difference between the two is that you see that A has a shorter ramp distance and B has a longer ramp distance. So that makes you think like, hey, maybe that would affect the travel, right? And also another thing that would be different between them is the angle of the ramp would be different, where B's ramp, the angle is smaller than A's ramp. So let's look at what velocity is relying on. So what sphere is traveling faster at the bottom? So we know that velocity relies on gravity and height. So is there a different gravity between the two? Not really, right? We're all on Earth. Is there a different height between the two? Not really. So they both start at the same height, therefore they will travel at the same velocity by the end of the ramp. So even though the ramp angle is different, it's still going to be the same velocity. So let's go on to letter B. Okay, number 6 says, consider the following variables that may affect the horizontal travel distance of the steel sphere rolling down an incline. So we're going to be doing the same lab that we have been doing. So just to recap, refresh your brain. The sphere is rolling down the incline. Whee! And we may even use a block this time instead of a sphere. And then it's on a table, and then it's going to travel in on a projectile path to travel at a certain distance. So this is the horizontal distance, where we can use v equals d over t, or we can use v equals square root of 2gh. So we have two velocities, two velocity equations that we can use. So we need to look at the mass, the release height, the angle of the inclined plane with respect to the table. So predict the effects of these three variables and what they will have on the sphere's horizontal distance. So last week we talked about the horizontal distance, and we learned how to find it when rolling a sphere down. But this time we're going to change 3 different variables, and you just have to predict it. So it's your hypothesis. You can use your if then because statements. So for example, if I make the mass of the object more heavy, then the ball will travel at a faster or slower velocity because so and so and so. And you can use your equations for your because, like because v equals square root of 2gh, and just explain further. Okay, so y'all know what y'all got to do? Yeah, any questions or anything? Okay, y'all can go ahead and get started.